Okay, great. Just very quickly, it's a real pleasure to introduce Ned Engelhardt, who's at MIT, and today she's going to you see the title there. She'll tell us about finding pythons in unexpected places, and hopefully we'll end up unconsumed at the end of this.
All right, thank you, Albion. It's of course wonderful to be giving a talk as part of the first day of the first symposium. I think the first symposium of this collaboration. So yeah, so this talk, I think the last talk was said to be a very practical talk. This will be an extremely impractical talk. This is well, I guess if you just look at the title, finding pythons in unexpected places seems like a pretty practical thing, but of course there's a lot of reading between the lines on this topic. So let me begin with just the outline of this talk and a bit of motivation. So this talk is centered around the information paradox, the black hole information paradox, which has been keeping many of us occupied in recent years. And of course, is one of the exciting aspects of the collaborations between quantum information and quantum gravity, which has been just so fruitful. And of course, is one of the tasks that we've undertaken with this consortium. So I'm going to talk a bit about the black hole information paradox. I'll kind of give a black hole information paradox in a nutshell, just the bare minimum that I'm going to need for this talk, and a little bit on the recent developments that are relevant for what I'm going to say. That came up a little bit in the last talk, this idea of coupling a black hole in two-dimensional gravity to an external system and evaporating it, and how much progress we've made on the black hole information paradox as a consequence of that. And then I'll talk about these more recent developments that's based on work with Jeff Pennington and Arvind Shabazzi-Moghadam, a couple of papers that came out in a few months ago. I don't remember at this point how many months. And also I might say a couple of words about some ongoing work. So let me begin with black hole information. So this is an example of the way in which quantum information and quantum gravity sort of come together. And this is really meant to be just the bare bones summary of some of the basic ideas that go into the information problem. So we imagine we take some pure state, we collapse it into a black hole. Now, before the black hole is formed, the entire universe is in a pure state. So the von Neumann entropy outside the black hole, where there's no black hole, so that's just the von Neumann entropy of everything in the universe. That's a pure state. That's the von Neumann entropy of our universe. That's 0. All right, I'll agree on that. Now, a fact that you need from semi-classical gravity is that black holes are thermal. They have a temperature, and that means that they can radiate. And in particular, what that tells us is that at intermediate times, we compute the von Neumann entropy of the black hole exterior, which is also what we call the radiation, and we get that this quantity is greater than 0. Now, if the temperature of the black hole is larger than the temperature of the surroundings of the black hole, then as the black hole radiates, it actually shrinks in mass. Since the temperature of the black hole, take my word for it, or I guess take Bekenstein's and Hawking's word for it, the temperature of a black hole is inversely proportional to its mass, then the black hole shrinks, it gets hotter, it keeps on evaporating until it disappears altogether. Now, after the black hole evaporates, and say, well, quantum mechanics is a unitary evolution theory, the time evolution operator is unitary, so that tells us the von Neumann entropy of the entire universe, once this process is done, should vanish again. That's just a statement of unitarity. We started out with a pure state, we evolved through some process, ended up with the pure state as long as it's a closed system. And the entire universe we expect is probably a closed system. So we expect to have an entropy at the end of the process, which is also 0. But if you do a semi-classical gravity calculation, in the regime where semi-classical gravity is valid, so we're not talking about a regime where we expect strong quantum gravity corrections, then you actually find that you end up in a maximally mixed state, which is, of course, a dramatic contradiction of the prediction of unitarity, which means that the von Neumann entropy has to end up back at 0. Now, I want to emphasize this wouldn't be such a big problem if this calculation ended up having to do with the very strong quantum gravity physics. In other words, if semi-classical gravity were to fail to predict unitarity in a regime where we don't expect it to be valid, then we wouldn't have a problem. But here we have semi-classical gravity in a regime where we expect that semi-classical gravity is valid. We expect effective field theory is a good theory, and it gives us a result which is in contradiction with what we expect from unitarity of quantum mechanics. All right, so this is how do we typically diagnose this? One tool that we like to diagnose, of course, is the von Neumann entropy, since it's not going to be 0 at the end if we end up in a maximally mixed state, and it will be 0 at the end if we end up in a pure state. So this is what Hawking's calculation would give us, that the entropy, the von Neumann entropy, increases, and it keeps on increasing until it plateaus once the black hole is finished evaporating, as opposed to the so-called Page curve, which predicts unitary evolution of the entropy, which means that the entropy would at some point have to turn over and go back down and eventually decrease down to 0. Now, the important thing here, of course, the deviations between the two curves occur already at these intermediate times, where you might say, oh, you know, at the point when the black hole disappears altogether, there's some strong quantum gravity physics, but we don't expect that in this regime over here. So again, this is a paradox because we have semi-classical gravity in a regime we're supposed to be valid, and its predictions sort of differ dramatically from the predictions of the unitary evolution. All right, next. Okay, so I'm actually not going to dwell, and go back one slide. I'm not going to dwell for too long on this. I'll talk a little bit about computing this curve momentarily, but I want to talk a little bit more about the two pieces of insights from quantum information into the information paradox, which are relevant for the recent developments on this front in holography. So the first one is the Hayden Preschool protocol. So this is essentially a protocol that tells us about information recovery from the Hawking radiation. So the protocol assumes that the black hole dynamics are drawn from a unitary 2 design. And the idea is if you throw in some state into an old black hole, and when I say an old black hole, I mean a black hole that's maximally entangled with this radiation. And here we imagine we throw in maybe some diary. That's kind of how the story typically goes. You throw in a diary into the black hole, some piece of information in some state. Then the information about the diary is going to be recoverable from the radiation. And this is going to be doable in a time that's logarithmic in the entropy of the black hole. Now, just to be clear, since I'm talking to a crowd of quantum information theorists, what by recoverable here, I mean that we can act with this operator on the combination of the early radiation and the late radiation. Here, this is a state of the black hole after it has radiated in the late radiation. And this here is the early radiation. And by recoverable, I mean that there exists there's an operator that distills the information in this way, where these are 1 and 2, these are factors of the Hilbert space of the radiation, both early and late. So this is the Hayden Preschool protocol, which of course is a very has been monumental in monumental development in the black hole information problem. Another, which I think has recently gotten more attention and keeps on getting more attention, or should keep on getting more attention, is Harlow Hayden, which is the statement that even if you could talk about decoding the radiation, whether it's plausible and whether it's possible, but then there's a question of, well, how hard is it to actually recover the radiation? And Harlow Hayden is essentially the statement that decoding the radiation is exponentially complex in the entropy of the black hole. And there's a slight refinement of this by Scott Aronson. The decoding the radiation is polynomially hard if there are no injective one-way functions, which I think is expected to be false. So essentially, another way of stating this is that the radiation is expected to be pseudo-random, that is exponentially hard to distinguish it from a Haar-random or maximally mixed state. All right, so this is the sort of two pieces of quantum information that are developments that are sort of more coming from quantum information that are very important for us on the black hole information front. Now, I mentioned that there were, I should say, if there are questions at any point, I'm more than happy to stop and answer them. Now, there have been quite a few developments that came up in the last talk, sort of as an aside, recently on black hole information in ADS-CFT. So I want to talk about those and then get more into the details of recovering the Hawking radiation and how complex that task is and how it geometrizes in quantum gravity. I think one of the aspects that have been most surprising and most insightful in the recent developments, and not just the recent developments, really in the past couple of decades, is the way that quantum gravity geometrizes information. And this, and how it geometrizes quantities and quantum information, tasks and quantum information. All of these have led to a lot of insights. And I think that's one of the reasons we've been able to make so much progress. So this talk is another talk about the geometrization of quantum information. And this one will be about the geometrization of the exponential complexity of decoding the Hawking radiation. But to get there, we're first going to have to talk about something that's a little simpler than the complexity, if you'll pardon the pun, the von Neumann entropy. So this is the sort of obligatory ADS-CFT slide. What is ADS-CFT? ADS-CFT is an equivalence between quantum gravity with ADS boundary conditions. Another way of saying it's quantum gravity in a box, sort of walls being an infinite distance away, and a lower dimensional non-gravitational quantum field theory. So here is a caricature. We have some D plus one dimensional string theory with anti-de Sitter boundary conditions. We call it the bulk. And we have a D-dimensional gauge theory that technically doesn't actually live on the boundary, but we call it the boundary anyways, because we're physicists and we're not super precise about things. So this is a duality between these two theories. It's an incredibly powerful duality because quantum gravity is often really hard, and quantum field theory, well, it also can be really hard, but at least there's no gravity complicating your life. So having this equivalence between them can actually teach you a lot about quantum gravity. It's very valuable. Now, one of the great statements about holography is that a black hole, at least a black hole in ADS, is just another quantum system. It's a quantum system of an ordinary non-gravitational theory. So really, it's just a black hole is really something pretty boring at the end of the day. An ordinary non-gravitational quantum system, and ordinary non-gravitational quantum systems don't have an information problem. Oh, sorry, go back to one slide. And that means that we expect that black holes at the end of the day, quantum gravity resolves the information paradox. And since ordinary non-gravitational quantum systems evolve unitarily, well, presumably so do black holes. Of course, we would like to understand a little bit better how that works. It's not good enough to just be sort of given from above that, well, ADS-CFT tells you that black hole evaporation process somehow has to be unitary. And I mean, that's great, but it doesn't actually help us understand why or what's the mechanism that implements that. So we want to have a more fine-grained understanding of how unitarity comes in to the gravitational theory. And that means, for example, being able to compute a page curve, which is consistent with unitary evolution of a black hole. And that's where the holographic entanglement entropy prescription comes in. Actually, I keep on going back to this slide, but I actually want to go back to this one more time. We know that if we do a gravitational calculation, we do Hawking's calculation in the bulk, we're going to get information loss. But fortunately, ADS-CFT gives us another way of doing a calculation that computes the von Neumann entropy. That it tells us if we compute the von Neumann entropy on the boundary, then we had better get unitary behavior. And that means that if we can translate the computation of the von Neumann entropy on the boundary to a computation that's gravitational in nature, then we have a gravitational calculation of a unitarily evolving von Neumann entropy, which is, of course, a step closer to understanding how quantum gravity mechanistically resolves the information paradox. So what is this prescription that relates entropy in the boundary to gravitational quantities? Well, if we work in a limit where the bulk is well described by perturbative quantum gravity, so I'm not claiming to do non-perturbative quantum gravity at any point in this talk, then it's given by the so-called holographic entanglement entropy proposal, which in a purely classical bulk is given by the Ryu Takenagi or Hubani-Magamani Takenagi. You add the first order quantum correction, it's Faulkner-Lefkowitz, Maldacena. You want to work to all orders in quantum corrections. This is work by myself and Aaron Wall. So what's the prescription? Well, if you want to compute the von Neumann entropy of a boundary state or density matrix, if you're looking at a subset of the boundary, then in the bulk, that's given by the area of a particular type of surface, which I'll discuss in a moment, over 4 in Planck units, plus the von Neumann entropy of quantum fields outside of that surface. So here is a surface. Here is the area of that surface, is just computing the area of this. This is everything outside of that surface, rho out, and we're computing the von Neumann entropy of that. the sum of these two is called the generalized entropy of that surface. And this surface chi, what is it? Why is it special? Clearly, it can't be any surface because this quantity will be different for different surfaces. So what makes this surface special is what we call quantum extremal, which means that if you take the surface and you wiggle it a little bit, then to leading order in the wiggles, this surface, this sum doesn't change. In other words, it's a stationary point of this, the generalized entropy functional. So you can just think of it as a stationary point, you shift the surface a little bit, it doesn't change to leading order. You might have more than one such surface, that's fine. In that case, we take the minimal one. So if we take the one that had the smallest value of the generalized entropy. Now the region that's between chi and the boundary is the part of the bulk that we can recover using quantum error correction, approximate quantum error correction. And it's the so-called entanglement wedge. So we call it the entanglement wedge, that's the region that can actually be, that is actually reconstructible. What I mean by that is you turn on some operator in that region, there exists a way of representing it in the dual theory. So what's today's talk? It's sort of a synergy, ADS-CFT, quantum information in the black hole information paradox. So I want to sort of emphasize there are a couple of different languages that are happening here. So the recovery of the information, the way it was phrased in Hayden Preschool, and complexity of recovery, the way it was phrased in Harlow Hayden. These are not really in the language of quantum gravity. These are in the language of ordinary quantum mechanics. These are not phrased in ADS-CFT. ADS-CFT means that we have a tool to translate these into gravitational quantities that can be very powerful. And the recent development, as a recent-ish since 2019, is not as recent as it used to be, even though I feel like the 2 years of the pandemic should kind of like hit a pause there. What's happened is we've understood how to geometrize both of these within ADS-CFT. So these are Harlow Hayden and Hayden Preschool are two quantum information theoretic advances on the information paradox that needed a gravitational interpretation in order for us to begin to understand how to use them to start thinking about resolving the information problem. And I would say the recent developments are really working towards that front. We understand better now what is the geometrization of Hayden Preschool. What do we mean by Hayden Preschool in gravity language? What do we mean by Harlow Hayden in gravity language? So these most recent developments that I'm going to talk about now from 2021, these are this statement, discovery, partial conjecture, partial proof, that the exponential complexity of recovery that is predicted by Harlow and Hayden for the Hawking radiation within ADS-CFT, actually there's one mechanism that is always responsible for it, and it's the same mechanism as in the case of Hawking radiation. In other words, there's a universality for when things are exponentially hard to reconstruct in ADS-CFT, and essentially it always boils down to Hawking radiation. So that's what I'm going to tell you about today. So that's the last section here, holographic geometrization of black hole information. And I will talk both about the geometrization of Hayden Preschool, which is, I guess, by now old news from 2019, and the geometrization of Harlow Hayden, which is more recent. So let's begin with the geometrization of Hayden Preschool. So in 2019, we computed the entropy of the radiation of an evaporating black hole in ADS, coupled to an auxiliary system. Jeff Pennington argued that this is true in general dimensions, and Ahmed Almhairi, myself, Don Merrill, and Henry Maxfield computed it directly for JT gravity coupled to a conformal field theory with an auxiliary bath, a conformal field theory in its ground state. Now, as I mentioned before, we're not going to use the Hawking formula minus trace rho radiation log rho radiation, because that is always going to give us information loss. Instead, we used quantum extremal surfaces to do this calculation. So we use this formula. The Neumann entropy of the boundary is given by the generalized entropy of the dominant quantum extremal surface, where the dominant one is the minimal one if there's more than one. And quantum extremal surfaces involve areas, and they involve Neumann entropies of fields propagating on our space-time, which in particular means that they can be computed without accessing strong quantum gravity physics. This can be a purely semi-classical effective field theory calculation. But I want to emphasize, this is not the usual semi-classical calculation. We have two different semi-classical gravity calculations that we can do. And one of them is consistent with information conservation, and one of them is consistent with information loss. Okay, so here's an illustration, which I like to put on slides just because it looks so nice, of the evaporation process. So here we have a black hole that formed from collapse. And the black hole, so here we have time running upwards in this diagram. We have a black hole that starts out as a star. And then as time runs forwards, this sort of starts to collapse and the force of its own gravitational field. This gray surface here is an event horizon, which forms sometime into the collapse. Inside, the black hole keeps on collapsing, a singularity eventually forms. Here you see the event horizon also begins to shrink at some point because the black hole is evaporating, and eventually the black hole disappears. There's some quantum gravity going on here. We don't know what that is. But what happens is at the page time, or after the page time where the turnover in the page curve happens, we get a new quantum extremal surface that forms here. So at early times, the dominant quantum extremal surface, the one that goes into this calculation, is the empty set. And after the page time, at the page time where we expect things to start to turn over, we expect to, if we have unitary evaporation, we expect that we eventually get some kind of a turnover. That's when we get this new quantum extremal surface, which sits just behind the event horizon. So this is a moment of time picture. This is rho out. This is the quantum extremal surface. It's just behind the event horizon. So this is a new quantum extremal surface. It's not close to any classical extremal surface. It's sort of this artifact of quantum corrections. And its generalized entropy decreases as a function of time. So this quantum extremal surface, this new one, this novel one, is kind of the reason that we get the turnover in the page curve, and this is what is responsible for the calculation that we can do in semi-classical gravity, which is consistent with unitarity. Now, what happens to the entanglement wedge? Well, the entanglement wedge of the boundary, not including the radiation, is everything that's between this quantum extremal surface and the boundary, which leaves a part of the bulk which is not in the entanglement wedge of the dual boundary, is not recoverable from the boundary theory. Instead, it was proposed by Jeff Pennington, Hari, and others that this is in fact the entanglement wedge of the radiation, so that you can reconstruct the radiation. You can reconstruct from the radiation anything that happens behind this quantum extremal surface. And part of the reason for this, of course, is that, well, if you can recover everything from here to here from the CFT not including the radiation, then, well, what's left over is something is what should be recoverable from the radiation. Now, why do I mention the entanglement wedge here, and why do I keep on emphasizing the fact that there are two quantum extremal surfaces here, the empty set and this one, and there was a shift in the minimal one? The reason I keep on emphasizing that is that if we had so erroneously kept on using the empty set as the minimal quantum extremal surface, if we maybe hadn't looked hard enough, didn't find this one, or we didn't know about the minimality condition in the quantum extremal surface formula, we would have gotten the Hawking curve. So this sort of raises the question of Vijay, yeah.
Yeah, can I ask a question?
Yeah.
It's a point that I keep getting confused about because the way people use language, not you, but everybody else who talks about this, which is when we say that the interior is an entanglement wedge and therefore reconstructible, is it the case or is it not the case that the action of an operator in the radiation is understood to act on the interior? What I mean by this is that usually if I say A encodes B, that means by looking at A, I know what B is. It doesn't mean necessarily that if I act on A, you act on B. But people are using that language all the time. So I'd like to understand what I should be thinking there.
Well, if you really genuinely think that the interior of the surface chi is dual to the radiation, then certainly whatever you do to the radiation will have a corresponding action on the black hole interior.
I guess that is what I'm asking. So in this picture, when we say that the interior is in the entanglement wedge of the radiation, do we mean that the radiation is dual to the interior? I mean, it isn't the dual to ADS. It isn't the, it may be weakly coupled. It may be free bosons floating around.
Yeah.
So that's what I'm.
Yeah, that's a great question. That's a great question. Yeah. So I think we use poor language to describe this. And part of the issue is this flat bath that we couple to the system. So the way I like to think about this is that we have two systems here, two genuinely separate systems. We have a quantum dot, which is coupled to a flat CFT, to some quantum field. There doesn't have to be a CFT, but let's take it to be a CFT. And then we also have our ADS bulk, which is also coupled to a flat bath. And I want to think of these two as two separate systems that are dual to one another. And then there's no confusion about how is it that you took some mode from the interior of the black hole, you exported it into the flat region, and then now it's dual, even though it came from the same system, and somehow it's dual to it, as if it were behaving as if it were the lower dimensional CFT. The way I like to think of this is I'm going to take my quantum dot, I'm going to couple it to a system. Then there's going to be some exchange between the quantum dot and the rest of my system. And that's what's dual to the black hole coupled to the bath. And I think in that case, there's no confusion as to, sure, I can do something in the quantum dot system that will result in something happening in the black hole coupled to the bath. But I agree with you, it's very confusing the way we talk about it, because we often kind of forget about the fact that they're really two separate systems here, and we need to treat them separately if we want to talk about duality.
Okay, thanks.
Okay, so the question that I want to bring up here is whether we can interpret Hawking's calculation as sort of using the wrong quantum extremal surface, which is, I should say, I'm not the first to ask this question. This is a very natural question to ask in the context of this calculation, that there's a novel quantum extremal surface that did the right calculation, and there's the old quantum extremal surface that we would have used if we didn't know about quantum corrections, if we didn't know about the minimality condition, that gives us the wrong answer, that gives us exactly what Hawking got. So, of course, at the end of the day, we want to understand what was Hawking's mistake. That's one way of approaching the information paradox, or maybe even resolving the information paradox. So let's ask, what are the two different ways that we have of computing the Hawking radiation? Well, we have the quantum extremal surface formula, or we have Hawking's calculation. And they give dramatically different answers. One is consistent with unitarity and one is not. And so to resolve the information paradox, or one way of approaching a resolution, is to ask, where do these two approaches diverge? How do we put these two approaches on the same footing so we know where we need to correct Hawking's calculation? Of course, they're in two different languages right now. One is holography and one is not. One is geometric and one is not. So we have to understand these a little bit better. Now, if you asked me before 2019 where Hawking went wrong in his calculation, I'm going to post-dict the past now and tell you that my answer would probably have been something along the lines of, oh, Harlow Hayden probably means that somewhere, somehow, Hawking's calculation lost track of any exponentially complex data in the state. Now, where does this intuition come from? It comes from the fact that it's exponentially hard to reconstruct the radiation. So if you somehow coarse grain over exceptionally difficult tasks, over exceptionally difficult, especially exceptionally complex information, then you're left with thinking that your state is actually just maximally mixed. So potentially Hawking's calculation could be coarse graining in some way that I haven't defined yet over high complexity data. All right, what about now? If you ask people now, most people would say something along the lines of, well, isn't it obvious Hawking used the wrong quantum extremal surface? Now, of course, Hawking didn't use quantum extremal surfaces. So let's give him some credit. He didn't use the wrong quantum extremal surface because he didn't use quantum extremal surfaces at all. Something else that people say is he used the wrong saddle in the gravitational path integral, which is essentially the same thing as saying he used the wrong quantum extremal surface. Now, just to be clear, I don't know where Hawking started to just indiscriminately say, I'm going to ignore all high complexity data, or, he didn't do this in the language of quantum extremal surfaces, but trying to put Hawking's calculation sort of on the same footing as the quantum extremal surface calculation could be very helpful in understanding better where he went wrong or what was missing from his calculation to see evidence of unitarity. So this idea of coarse graining over complexity is going to keep on coming up. But the question that this brings up, of course, is how do we reconcile these two perspectives? We have coarse graining over complexity, and we have using the wrong quantum extremal surface. And we want these two to somehow mean the same thing if both of them are right. Both of them are doing the same thing. If both of them are what Hawking did wrong, well, I don't know, have a lot of faith in Stephen. I think he probably only did one thing wrong. And so it's one of these. Which one is it? Maybe it's the same thing. Is there a way of thinking of using the non-minimal, the wrong quantum extremal surface as a geometrization of coarse graining over complexity? Are these two the same thing? Is using the wrong quantum extremal surface the same thing as coarse graining over complexity? That's the geometric interpretation of coarse graining over complexity. And in fact, I would say that the answer to that is yes. So in 2017 and 2018, which is definitely prior to these exciting developments, Aaron Wall and I proposed that if you only have access to the expectation values of simple operators, then that's the same thing as only having access to the fake entanglement wedge of a non-minimal quantum extremal surface. So there's a sense in which this is exactly the geometrization that we're looking for, that if you don't know about exponential complexity, then you don't actually have access to anything that lives not in that lives in the entanglement wedge of the true quantum extremal surface, but not in the entanglement wedge of the non-minimal quantum extremal surface. Now, the way we phrased this was in a somewhat different language. It was formalized very beautifully by the so-called Python's Lunge proposal. So it was all tied together in the context of these new developments, in the context of quantum extremal surfaces being different from classical extremal surfaces. This was by Adam Brown, Karan Garibian, Jeff Pennington, and Lenny Susskind. And they proposed that whenever there exists a non-minimal quantum extremal surface that lives inside of the entanglement wedge, then reconstruction is exponentially complex. So let me unpack that a bit. So and also explain why it was called the Python's Lunge. So here we have a moment in time of the black hole geometry. Here, this is a two-sided black hole, so this is meant to be the maybe a moment of a slice of this space-time here. This is the minimal quantum extremal surface right here. There is a non-minimal quantum extremal surface here. And there's also a bulge between them. And apparently Lenny and friends thought that this looked like a Python's Lunge, although it doesn't look anything like a Python's Lunge to me. And so this became the Python's Lunge proposal, where they said that the complexity of reconstructing anything that lives behind this non-minimal quantum extremal surface here is exponential in the generalized entropy, in the difference of generalized entropies between the bulge and the generalized entropy of the surface here, which Jeff and Arvind and I call the appetizer. So this is a geometrization of Harlow Hayden, you could say, because this region here is what we expect to recover from the Hawking radiation. This is the this is the island, and so this is what we expect to recover from the Hawking radiation. We expect that it's exponentially hard to reconstruct this region, and this is what they proposed is what quantifies that. And this non-minimal quantum extremal surface is essentially what tells you the reconstruction is going to be exponentially complex. Well, this is great. It's a very beautiful picture. And it was motivated by a tensor network picture of this sort of bulk to boundary map. So here we have a caricature of a tensor network. This isn't an actual concrete model. This is just meant to be a caricature. There's no sense in which I know what each one of these tensors is. It's just the number of legs, meaning whether the tensor is an isometry or a unitary or not. So in order to do bulk reconstruction, what we essentially have to do, we have to go from the minimal cut. We want to push from the minimal cut to the boundary, which sits over here. And so here we have to push through to these isometries over here. And then we have to push through these. And these are not isometries, right? These are the ones where you take two legs and they go to one leg. So this is actually post-selection here. And post-selection, we know from Grover search is, it's exponentially complex in size of the Hilbert space. So even though in order to actually have bulk reconstruction, to have the ability to push from this to the boundary, you need this whole tensor network to be an approximate isometry. You don't need the individual tensors to be isometries. And that's where the Python's Lunge comes in, right? This is a constriction. You have fewer legs here than you do here, but there's still more legs here than there are here, which means you can reconstruct this region over here. And this bulge is in the tensor network is kind of what motivated him to look at a bulge in the Lorentzian space-time geometry. So this constriction is very important, and the constriction in this lunge is due to post-selection, which is where the exponential complexity is coming from. Now these dots here, these are meant to denote what we call bulk legs. These are the degrees of freedom of the bulk quantum fields. All right, so that's great. It's very insightful, but it's not quite good enough for what we want. We want to literally identify Hawking's calculation with complexity, with the coarse-graining over complexity. And so that means we have to go both ways. We have to show not only that quantum extremal surfaces, whenever you have a quantum extremal surface, you have exponential complexity. But whenever you have exponential complexity, you also have a quantum extremal surface, a non-minimal quantum extremal surface. In other words, we want to literally identify non-minimal quantum extremal surfaces as the geometric avatar, the dual of exponential complexity, which means it has to go both ways. Whenever we have one, we have the other, and also the other way. So what Arvin and Jeff and I proposed was this, what we call a strong Python's lunge, which is that non-minimal quantum extremal surfaces are in fact the only source of exponential complexity in the ADS-CFT dictionary. So not just that they are a source, but literally the only source. And this is what would allow us to then identify coarse-graining over complexity as literally identify that with not having knowledge of what's behind the non-minimal quantum extremal surface, because it tells us that whenever there is exponential complexity over which to coarse grain, there is a non-minimal quantum extremal surface that can act as that geometric avatar. So this is the strong Python's lunge proposal, I should say, which is proven in some cases, and we were able to give a strong argument in other cases. Okay, so first of all, before I go into the argument, I won't go through the proof. I'll go through some, question.
Netta, so this exponential complexity in the case of Hawking radiation from a regular black hole, what is the non-minimal quantum extremal surface in that case?
Excellent question. And if you'll just hold on, the rest of my talk is about that.
Okay.
Yeah. I'm so glad someone asked, because they give me the excuse to talk about it. So actually, this is the slide that starts to talk about that. So okay, so if we have a system with a gravitational dual, semi-classical gravity dual, and we know that there's some information that whose recovery is exponentially hard, then we immediately know by this proposal that there has to be a non-trivial quantum extremal surface. Now, I think Vijay was probably starting to allude to this, which is that compact quantum extremal surfaces actually only exist when there's a future and a past singularity. This asterisk here is meant to be the rest of the talk. And the bulk dual to complex systems like that, it has both a future and past catastrophe. And so we, as I'll mention shortly, we certainly know that black holes can form from regular initial conditions. And that seems a little bit, a little suspect. I'll get back to that in a moment. But assuming that I can convince you that that is actually not a problem, then this conjecture gives us a huge amount of control and an understanding of universality of difficult tasks in the dual theory. How frequent are these non-minimal quantum extremal surfaces? When do we find them? What does that mean about exponential complexity in the dual theory? This sort of goes both ways. Okay, but this asterisk is kind of important, and there are plenty of apparent counterexamples, which Vijay was thinking of, but was too nice to say in that way. So let's take a step back here. I just said that non-trivial compact quantum extremal surfaces will only appear in spacetime that have both a past and a future singularity. Now, let's take a garden variety black hole, and we're going to make it very simple. That was not meant to be a pun. It's a stable black hole. It's not evaporating. There are no extra complications. We have reflecting boundary conditions. These are not transparent. They're reflecting boundary conditions, and it formed from collapse. There's no singularity in the past that's necessary here. Is any of the bulk exponentially hard to reconstruct? Yes, most definitely. There is a part of the bulk that should be exponentially hard to reconstruct. So we have this black hole. It has a temperature. It's not evaporating, but it's still going to have Hawking radiation. And here we have modes that are straddling the event horizon. And we can trace them backwards in time, and they will become trans-Planckian, and we expect that that's going to be very, very hard to reconstruct. So by the strong Python's Lunge proposal, that means we should see another non-trivial quantum extremal surface here in this space-time, which has a regular past and no past singularity, and it appears we have a contradiction here. Exponential complexity of reconstruction, but apparently no quantum extremal surface. So what gives? Parent contradiction. Well, we're going to have to take a step back to understand what's going on here and see that there is a sense in which there's a quantum extremal surface here. So let's take a detour into bulk reconstruction first, because there's a subtlety there that allows us to explain a lot of things that will come up here as well. So let's take a step back and talk about reconstruction of the bulk within some code subspace. So we're going to consider some, so this is your standard moment in time, ADS CFT. We have some boundary region R. We imagine we turn on some operator phi of x. Now, when we talk about bulk reconstruction in ADS CFT, we talk about quantum error correction, and we talk about it, of course, within some code subspace. Now, when we talk about turning on some local operator, that action is only defined within a code subspace of states, where we have these quantum fields on a particular semi-classical background. Right? This being a local operator, that only makes sense in some particular small code subspace where we have some particular space-time geometry. Now, within this code subspace, we want to reconstruct this object from the density matrix of rho R, from the state on rho R. Then we need this to lie in the entanglement wedge of R. In other words, this is the quantum extremal surface. This is the entanglement wedge. This has to lie in the entanglement wedge in this code subspace. But of course, since this is a quantum extremal surface, its location depends on the entropy of bulk quantum fields. It depends on the bulk state, right? Since these are defined using not just the area, but also rho bulk. Okay, so it's possible to, okay, I'll go through this a little bit in detail. If we want to reconstruct, acting on, we want to reconstruct phi of x, well, that means that both the bulk state before we turn on this operator and the state after we turn on this operator have to both be within our code subspace, and phi of x has to lie in the entanglement wedge. So in other words, we cannot have a situation where changing the state as a result of acting on with this operator actually moves the quantum extremal surface around to the point where that operator doesn't live in the entanglement wedge anymore. So for example, what if the quantum extremal surface that extremizes this is not the same one as the one that extremizes that? And what if the first surface, the one that extremizes this, contains the operator in its entanglement wedge, but once we act with the operator, actually, then this quantum extremal surface doesn't contain it in entanglement wedge anymore. This appears to be very confusing, and this was explained in a very beautiful paper by Hayden and Pennington, where they said, all right, if you want to define a state-independent but code subspace dependent reconstruction, so you want to fix your code subspace and define a state-independent reconstruction, then you can only consider operators and fields that lie in the entanglement wedge when the bulk state is maximally mixed. When the bulk state is maximally mixed, in some sense, everything that, so if this is the quantum extremal surface for the maximally mixed bulk state within your code subspace, so this is not maximally mixed in the entire Hilbert space, but maximally mixed in the code subspace, then every operator that you turn on here will be reconstructible in a state-independent way. And so the relevant quantum extremal surface for bulk reconstruction by approximate quantum error correction is the quantum extremal surface that is evaluated by extremizing A over 4 plus S of the maximally mixed bulk state in the code subspace. So the maximally mixed state is extremely important for purposes of bulk reconstruction. All right. Now let's go back to the Python's Lunge. What we're going to see is that the maximally mixed state strikes again here. So we're going to have to work a little bit hard to do this. I think Peter said in his talk, there's no such thing as a free lunch. And this is a lunch we're going to have to work hard for. So here we have this again, this tensor network caricature of the Python's Lunge geometry. Now, we want to be able to reconstruct a particular operator. And that means that the operator has to lie in the entanglement wedge. So it has to lie somewhere between gamma min and the asymptotic boundary. Now, if we want to reconstruct an operator that lies between gamma min and the appetizer, then the condition is that this gamma, the area of the appetizer, so this thing here, has to be larger than the area of this in the maximally mixed state, meaning plus the log of the dimension of the bulk legs coming out of the page. So this is the condition for reconstructibility of an operator here. If this condition is violated, then we have a situation where there's, in the maximally mixed state, this appetizer surface is in fact minimal. And that is the appetizer, that is the actual the quantum extremal surface of the that dominates. So we do not want that to happen, which means that this, which gives us this condition over here. Now, another way of rewriting this is that in the maximally mixed state, the generalized entropy of the appetizer has to be larger than the generalized entropy of our quantum extremal surface here, which guarantees minimality of this, which means everything on this side can be reconstructed from the boundary. So this is just a statement that gamma min is the minimal QAS, which we can repackage in this way in this Python's Lunge geometry, in this caricature. Okay, now why is this relevant? Because we basically argued that the similar case holds for complexity. The same thing as reconstruction. You have to consider it in the maximally mixed state. So it's easy to see from the tensor network picture. So the constriction here in the tensor, the cause of this is exponential complexity. And it depends. The constriction depends both on the number of legs that you cut, and the number of in-plane legs you cut, and the number of bulk legs that you cut. And that means that you actually have to evaluate this in the maximally mixed state where you cut all the bulk legs and not just a few of them. So what we concluded from this is that complexity of reconstruction is determined by the non-minimal quantum extremal surface in the maximally mixed state in the code subspace. So when we say that it's exponentially hard to reconstruct something due to non-minimal quantum extremal surfaces, implicitly what we're referring to, what we mean by non-minimal quantum extremal surface is non-minimal in the maximally mixed state. So why does that help us? Well, let's consider building a code subspace and taking the maximally mixed state. So we imagine we're working with some black hole that's sort of more or less reached equilibrium at this point, formed from collapse a long time ago, and it's not evaporating, it's more or less at equilibrium here. And we look at a code subspace of states with this fixed geometry. We look at the Hawking modes, straddling the horizon in this sort of adiabatic approximation, and we ask, in a maximally mixed state of this code subspace, in a situation, in other words, in the state where these two modes are disentangled from one another, is there a non-minimal quantum extremal surface that lives sort of flush up against the event horizon that will tell us that these modes here are exponentially hard to reconstruct? That's what we need in a maximally mixed state. And the answer is that yes, there is. So what happens is the maximally mixed state has reduced entanglement. These two end up being disentangled because now they're maximally mixed with another system. And this basically, in the exact same way that it works for the page curve, this results in very large entropy gradients. It nucleates a new and non-minimal quantum extremal surface that basically sits on the event horizon in the maximally mixed state. And so you find that in a maximally mixed state, everything behind the horizon is exponentially hard to reconstruct. Exactly what we expect, of course. Now, we still have Vijay's question to address, which is, well, what about the past? Doesn't have to be a past singularity. Yes, there does. And in fact, what happens is when you disentangle these modes and then you evolve backwards, you end up getting a past singularity. So we start out with some code subspace of states that we define at some late time. Then we evolve backwards. The fact that we disentangle these modes leads to a past catastrophe, a white hole singularity. And this exists in a maximally mixed state. So the fact that we're using the maximally mixed state means that we get around this issue where we have this black holes that form from collapse that have a regular past and exponential complexity. But the maximally mixed state of any reasonable code subspace that we want to reconstruct will have a quantum extremal surface and will also have a past singularity, making all of this consistent. So the actual version, the actual statement of the strong Python's Lunge is that non-minimal quantum extremal surfaces in the maximally mixed state of the code subspace are the exclusive source of exponential complexity in the ADS-CFT dictionary. So that is the final statement of the strong Python's lunge. All right, so as I think I'm probably, I've actually got a little bit of time left, but let's try to finish. Okay, so a few parting remarks here. Well, we proposed this strong Python's lunge. Non-minimal quantum extremal surfaces are the exclusive source of exponential complexity within ADS-CFT, again, within the maximally mixed state, which is very similar to the way things work for bulk reconstruction. And of course, for me, the reason that this is so interesting and so important is that this provides a way of bridging this two different ways that we have understanding how Hawking was in some sense was wrong. He used the wrong quantum extremal surface or the wrong saddle in the gravitational path integral versus he didn't know about Harlow Hayden, so he lost track of anything involving exponential complexity. The strong Python's lunge and the ordinary Python's lunge together give us a single unified packaging of how to geometrize that statement. There's a single unified way of explaining what is the sort of ADS-CFT version of what Hawking did wrong. If you want, whether you want to call it coarse graining over complexity, or you want to call it using the wrong quantum extremal surface, these are one and the same thing. Now, what's the status of the strong Python's lunge proposal? Well, in the purely classical limit, we can actually, I want to use the word proof, but I want it understood that I'm using it in the context of a physicist's proof here, not at the level of a mathematician's proof. We have a physics proof for the strong Python lunge in the classical limit, purely classical limit. And so when I say purely classical, I mean when there's no back reaction. We ignore back reaction from quantum fields. So this is something that we can more or less prove. Now, of course, once you start adding quantum corrections, it's very hard to prove anything. But we do have this earlier analysis that I alluded to and discussed briefly, that any obvious counterexample, like the black hole formed from collapse with the regular past, you can do this simple analysis of just working in the adiabatic regime and show that there actually is a quantum extremal surface in the maximally mixed state. So essentially all we assume is that we have this, we're working in a regime where the black hole has more or less settled down, and that's an appropriate approximation. If you have a black hole that's constantly evolving and constantly absorbing stuff, then okay, analysis doesn't work. But if you allow your black hole to relax at some point, then our analysis will work and will show that there is a non-minimal quantum extremal surface in the maximally mixed state of the code subspace of Hawking modes across the horizon. So some questions regarding this and moving forwards and looking to the future. This is all great for understanding where Hawking went wrong in our language of ADS-CFT, but at the end of the day, it'd be nice to also understand where Hawking went wrong in Hawking's own language. So that's an outstanding question. How do we sort of see the signature of the non-minimal quantum extremal surface and exponential complexity in Hawking's original calculation? Which, and there's another way of saying this, it's how do we see the actual minimal quantum extremal surface in a language of semi-classical gravity that doesn't involve something like ADS-CFT? Another question I'd like to ask, as I should mention, this is work in progress with Lisa Yang, who is a graduate student in computer science at MIT. Harlow Hayden and Hayden Preschool assumed that unitary two designs are a good description of the black hole interior dynamics. This is consistent with that when they get things that are consistent with what we see in ADS-CFT. But is there a particular reason to believe that it's unitary two designs, or are there other models that model the interior black hole dynamics just as well? Maybe something like a pseudorandom unitary, or quantum encryption protocols. Are these consistent with the extant holographic results? Can we get more insight into the interior black hole dynamics by enumerating all of the different possible models that all result in something like a Hayden Preschool or Harlow Hayden that's consistent with the ADS-CFT results we've seen to date? And so I think with that, I will stop here and thank you for your attention.
Thank you, Netta. That was awesome. Any questions?
I think Matt has a question.
Matt has a question.
Yes. And then I have a question.
Yeah, thanks, Netta. That was great and super useful, especially for those of us who maybe haven't been following the Python's lunch story as much as we should. So I have a couple of remedial questions about the Python's lunch. So the first question is, in your picture, there was like a narrow neck, which was the actual quantum extremal surface, then a bulge, then a wider one, which was the fake one.
Yeah.
But of course, in between in the bulge, there was also a quantum extremal surface that was like a maximum.
Yeah.
So are those supposed to mean anything or not? Or do we, or is there some stability criterion and we just toss those in the garbage?
So let me just quickly go to the picture. Yeah, this one.
Yeah.
So the bulge certainly means a lot in the sense that it goes into the formula for exponential complexity. So the larger the bulge is, the higher the complexity. Of course, what you're really interested in is the difference between these two generalized entropies. But so if you have a very narrow neck and a very large bulge, it's going to get progressively harder to do reconstruction. So the bulge is very important, and it's certainly not something that we toss into the garbage.
I see, and it's defined by the unstable quantum extremal surface. I mean, is that the definition of X bulge or?
So that's a very good question. So I should say, so Jeff and Arvin and I are currently working on a maxi-max or a maxi-mini, I forget how many of those we have tacked in there, formulation of the Python's Lunge that would actually identify the surface independently of quantum extremality criteria.
Okay.
It is unstable. But what's kind of interesting is that it's not obvious. So this one, the first surface, you could imagine having sort of multiple bulges.
Yeah.
And while we know that the first constriction is stable and the first bulge is unstable, in fact, we can't actually prove that this remains the case when you have multiple changes. And in fact, we seem to be finding that there exists a situation where you might have two time-like separated constrictions. And so there are quite a lot of subtleties on understanding the geometry of this Python's Lunge. At least when there's just one bulge, it's quite clear. But there are many cases where you might imagine there's more than one. If you act with a lot of random unitaries, many different steps, you could imagine creating many different bulges. So this is kind of, it's a work in progress, understanding this geometry better.
But aren't there also cases, and I'm just thinking of like simple cases where RT has phase transitions where there isn't actually a maximum because the two phases have different topologies and they're both local minima and there's no maximum, there's no actual surface that's a maximum between them. So then, then what am I supposed to do?
Well, okay, at phase transitions, I think there's a kind of a, I mean, honestly, I don't know what to do about quantum extremal surfaces in phase transitions either, because
I'm not saying when you're sitting on the phase transition, but I mean in that sort of situation, we can definitely be on one side of the phase transition. We're not sitting on top of the phase transition, but there will be a fake minimal surface, if you want to call it that.
Yeah.
There will be no bulge.
Well, so I don't think that you can have a bulge that's not necessarily extremal, is maybe what you're saying, but it's extremal in one direction, but maybe not extremal in other directions. Because if you have a fake minimum, and then, so this is a sort of decreases and increases again, and you have an actual minimum, it's going to decrease again. And then there has to be, intermediate value theorem.
But that's not really true in general. I mean, that's true in this kind of simple picture you've drawn, but in cases where the two have different topologies, that's not true. I mean, so there, like in the usual phase transition with two intervals, blah, 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 there's no like maximal geodesics connecting them because the two minimal ones have different topologies.
Right. So you have a couple of choices in that situation, and we're honestly still figuring out which one is the right one.
Okay.
So I'll preface this by saying, the Python's Lunge geometry needs to be much better understood. But you have two options. One is to take your so you have basically an X min and an X, and you don't have a Lunge. And one of them is to essentially say, okay, we're going to consider one of them to sort of act the part of the Lunge. And you have to figure out which one is the appropriate one. Essentially, you would take the difference between the generalized entropy of that and the generalized entropy of that. And sometimes that seems to yield the right answer. Or there's a more general case. Well, do you need to consider some kind of deformation in time, and you need to worry about covariant considerations? And I mean, honestly, I think there's something that we're still figuring out.
Right.
The
I see.
thing which is certainly what I can tell you is absolutely clear and understood is the existence of this appetizer surface, in the sense that there's always an outermost quantum extremal surface. It might be the minimal one, it might not be the minimal one, but there always exists one, and it's always stable.
Okay.
So not much we can prove.
Okay. And can I just follow up with one other quick question? You're talking about a situation where the non-minimal one is inside the entanglement wedge, but it could have been the other way around. In
which case we don't care about it. Yeah.
Oh, you don't care. That doesn't mean anything.
Well, because the region that's important is the one that's in the entanglement wedge, because it's reconstructible. As soon as it's not reconstructible, it can't have exponential complexity of reconstruction because it's not reconstructible in the first place.
Oh, I see. So non-minimal extremal surfaces outside the entanglement wedge just don't mean anything.
Well, I mean, if you're working in a regime where you have complementary recovery, then that means something for the other side.
I see. Okay.
Yeah.
Thank you.
Yeah.
I'm going to go. There's three of us, so I'll go first, and then Elliot and Vijay probably, because I'm going to have to leave sooner. So I was actually going to ask something similar, and maybe you partially answered that, which is that there are another case where non-minimal surfaces seem to be important, or in say conical deficit geometries of ADS3, these things that show up in entwinement that Vijay's looked at. So I'd been wondering if those were relevant in this case, but maybe is it the
I haven't thought explicitly about that. So I don't know how intelligent my comment is going to be.
I'm not sure my question is intelligent, so it's all good.
I would say whenever you have, so I can tell you in the classical limit, I can tell you what we were able to prove. So, I mean, and since I think you're talking about the classical limits, maybe that'll help.
Sure.
We were able to prove that by turning on causally propagating matter and potentially time folding it a polynomial number of times, you can reconstruct all the way up to the outermost non-minimal, up to the outermost extremal surface, be it minimal or not.
Okay.
And conversely, you cannot go any further.
Okay.
So that means that any reconstruction you want to do beyond it is going to involve matter turning on something which is not going to propagate causally, which we would expect would not be simple, polynomially simple.
Right. Okay. Thanks. I'll sit on that and think about it. Elliot, I think you're next.
Yeah. So I just have a quick question about like your last slide. Where you were saying that that it would be good to like find where Hawking is wrong without appealing to ADS-CFT or something along those lines.
Yeah.
And it seems to me that, I mean, I'm kind of outside of this field, but my understanding is that the ways of computing the entropy using the Renyi entropies that involve replica wormholes, that doesn't really require ADS-CFT. That's at least my understanding.
Yeah, so I don't mean not using ADS-CFT, I mean using Hawking's language. So Hawking didn't use the gravitational path integral. So while I'm very sympathetic to what to the statement people make, which is he used the wrong saddle, the fact remains he didn't actually use the gravitational path integral. He used a bunch of Bogoliubov transformations, and I don't know what was wrong with those if effective field theory is valid at the event horizon. So I would like to understand what actually went wrong in Hawking's calculation in that language, or if nothing goes wrong, then basically what are we missing in that language? And since he didn't use the gravitational path integral, I don't think that's not quite a satisfactory answer for me.
Well, couldn't it be though that he was like treating the geometry as fixed and classical, and that's what you're missing when you like ignore the other saddles?
Well, the problem is saying the geometry is dramatically changing or is non-classical is a way of saying you have large violations of effective field theory at the event horizon, which is not, that's not consistent with the fact that we have small curvature at the event horizon. So we expect that there's a decoupling, an effective decoupling between gravity and quantum field theory at the event horizon.
But if you look at the gravitational path integral and you find contributions from solutions other than the classical solution, isn't that saying that those other geometries are important?
So those are exponentially suppressed, right? And you have to keep in mind that they dominate in the replica trick, but that's not quite the same thing as saying that the space-time geometry literally looks like that. And I in particular, I would argue that, sure, the replica wormholes suggest that there's some non-perturbative corrections that are coming in, but we have to then understand how those can possibly come in without violating effective field theory.
Yeah. Okay, thank you.
Mhm. Is it Vijay or Adam who's next? I think it might be Vijay.
I'm going to defer to Adam first because I asked questions already and Adam didn't.
Okay.
Okay, great. Thanks. Yeah, so I have, if you'll indulge me, 2 questions. The first is just to make sure I understood your result, and the second is more future directions.
Mhm.
So if one wanted to prove this strong Python's lunch kind of proposal, would it suffice to give like an explicit quantum algorithm that performs bulk reconstruction and runs, in quantum polynomial time, and the only time it doesn't is when, there's one of these surfaces? And then if that is correct, is there any hope or prospects for doing something like that?
So that would be part of it. So to give an actual proof, we would have to consider all possible, an arbitrary bulk geometry, a semi-classical geometry with an arbitrary quantum field theory on it, and prove that this is always the case. And even if we allowed ourselves to make assumptions like maybe the quantum focusing conjecture, which is, I would say, is a pretty valid assumption, we would still have to somehow, we would have to consider all possible, code subspaces, and I would say, I'm not too bothered about the fact that we don't have a proof, because I think that in our argument we captured the sort of the most likely cases where the cases where it's most likely to fail, and I feel it's a fairly generic statement I would say that we have, but I just wanted to emphasize the fact that I don't want to claim that it was a proof, because that's very difficult to come up with a general proof in this kind of regime of quantum gravity.
Sure. And yeah, and just so I understand, it sounds like you're saying it's difficult because it would require some like enumeration or classification of all valid theories or something like this, which that sounds pretty hard. Yeah,
it sounds hard.
Cool.
Somebody else can do it.
Sure. And then my second question is, I'm just kind of curious about if there are any other connections to cryptography that could be derived from this work. So, in general, in my paper with Bill and Umesh, where we were trying to argue for exponentially hard reconstruction, we ended up locating the hardness in the very computational notion of, it's hard to break a block cipher. Like this is like very cryptographic idea. And then, now you have many other scenarios where you believe there's this exponentially difficult reconstruction. Is there any sort of like quantum cryptography or some sort of insights we could gain from this?
That's great.
It's a very broad question, but
it's a great question though. So first, let me address the very first part of what you said, which is that your setup does have a non-minimal quantum extremal surface in the maximally mixed state, which is which means that it really actually lives on kind of the same plane as as what we were using for the definition of exponential complexity. Now, with regards to whether there's a quantum cryptographic statement we can make here, it's very aesthetically appealing to think that the answer is yes. That there is a way of thinking about this from a quantum cryptography perspective. I should also mention that in this work I briefly alluded to with Lisa Yang about talking about the interior dynamics of the black hole, we are thinking about various different quantum cryptography and encryption algorithms for how that might work. And in particular, what do you want? You want to generate a pseudorandom state. And then many different ways of, but okay, I should say, one thing that has bugged me a lot about the quantum information literature and the high energy theory literature is that when we say pseudo-random, we typically mean indistinguishable from a maximally mixed state. But in quantum information, it means indistinguishable from Hall random. And that's actually like a very big gap. And it's not clear to me why. It's a huge gap, right? And so, and we're sort of, I guess I should say, like this work with Lisa, we're kind of hoping to capitalize on that gap. And see, does quantum gravity actually need the state to be Hall random, or does it need the state to be maximally mixed? And if it needs the state to be maximally mixed, there's kind of actually a lot that you can do that's not limited to unitary 2 design. Potentially, I should say potentially. It's work in progress.
Like all sorts of like pseudo-random unitary construct. Like I think
exactly,
really cool. Yeah, if you can come up with some new like quantum gravity inspired pseudo-randomness constructions, then
because I mean, so far, I mean, correct me if I'm wrong, but I think I have only been able to find 2 constructions of pseudo-random states in the literature, and one of them is basically saying that instead of roots of unity, you could just put a -1 in. So really, just one construction of pseudo-random states, and it doesn't. For that construction, it's kind of it's very robust, right? It's a Hall random, and Hall random against. And it's protected against many shot decryptions. So it's very different from what we expect of the Hawking radiation. It's much more random than what we expect from the Hawking radiation.
Yeah, exactly. Yeah, well, yeah, and then the kind of block cipher based things that I have with Umesh and Bill, that's also pseudo-random state construction, but you can't reduce it to some kind of standard cryptographic thing like Giglio and Song or the Brikursky paper that you're referring to do.
So I think that there are a few gaps here, and I think that the question that that Lisa and I are asking, essentially, what does quantum gravity actually need here, insofar as the type of state, and is it pseudo-random? In what sense is it pseudo-random? Like something is exponentially hard, but what?
Exactly. Cool.
Yeah, so it's a work in progress. So could be a while.
Awesome. Looking forward to seeing that. Cool. I'll now defer to Vijay to ask his question. Thanks for patiently waiting. So.
Great. That was a very interesting question. I have 2 or 3 small points of clarification. A few slides ago, you have a picture where you say C, the complexity is related to whatever the size. That one. So the first point of clarification that I'd like to ask is.
Sorry, I'm getting there.
Probably.
It's a bit up.
Almost there.
You can keep asking while I'm scrolling.
So what is the definition of complexity there?
Oof. Well, what we mean here is defined in terms of unitary 2 gates. If you wanted to prepare.
Okay.
Yeah, if you want, it's a reconstruction complexity. So if you wanted to, if you wanted to reconstruct some operator in the interior, you want to take your state, you put a bunch of unitary 2 gates, and this proportionality here is because we're agnostic about whether the prefactor that comes in is volume or action. Probably one of the 2. Yeah.
Okay. So now, if I have a bag of gold geometry, so the x min on the other side is 0, what would I say in this kind of language about that?
So you would say that any operator inside the bag of gold is going to be exponentially hard to. If you turn on an operator inside the bag of gold and you want to do reconstruction in the dual theory, then it's going to the circuit that you have to construct to implement the reconstruction is going to be exponentially complex in terms of size, and the complexity is what goes in the exponential will be the difference between the throat of the bag of gold and the place where it's largest.
So in this case, the size of the non-minimal extremal surface is in this way directly related, well, not related to entanglement entropy, it's related to a reconstruction complexity.
Yeah, exactly. And you'll notice that the minimal one doesn't enter here at all. The minimal one is only important insofar as knowing that you can do the reconstruction. Once you know that, then you can forget about it. Okay, so I have a couple of questions then about a construction I've been doing with de Sitter space, which I will send you separately to. Okay. Because de Sitter space, I'm terrified already. Yeah, no, everything about de Sitter space is terrified. I've been terrified. I've been terrified about de Sitter space for 20 years. It just gets worse.